This is the capacitor. It consists of two metal plates separated by a dielectric insulating material. Its main characteristic is the capacitance value. This value is a measure of the amount of electric charge that can be stored in the component. Hence, it can be charged by the electric network or discharge its energy into the same network. As a quick example, I can show you here a simple LED circuit without a capacitor. As you can see, as soon as I turn the power source, the light emitting diode will emit light or stop in an immediate response. In this next circuit, I have put a capacitor in parallel. When I connect the power source, the LED will turn on, but also the capacitor will charge with energy. Initially, there is no potential difference between the capacitor metal plates. But when I connect the power source, the plates assume the same potential as the terminals, so a potential difference now exists between the capacitor plates, and the component will assume the same terminal voltage as the voltage source. The quantity of charge stored depends on the dimensions of the plates and insulating material, as well on the power supply voltage. When we disconnect the power source, we can see that the LED remains on for a while and slowly turns off. This is because the capacitor is discharging its accumulated energy into the network, feeding the LED. Eventually, the capacitor will discharge and stop feeding the LED. Please bear in mind, a capacitor cannot be treated as a voltage source. The current flow from the capacitor will rapidly decline when the electrons are transferred between plates. On the other hand, a voltage source tends to keep a steady power supply while connected. There are many types of capacitors. Currently, I have with me ceramic capacitors. Metal plates are placed on each side of a thin ceramic disc, and terminals are connected to the metal. The entire unit is encapsulated in a protective coating of plastic. Electrolytic capacitors. Two sheets of aluminum foil are separated by a dielectric material and rolled up and encased in an aluminum cylinder for protection. It is very important that the electrolytic capacitors are connected with the correct polarity. When incorrectly connected, gas forms within the component and it can lead to an explosion. The behavior of the capacitor in the electric network is much different from a resistor, and some advanced calculus is involved, but some basic calculation formulas are as follows. The capacitance equation is above. Epsilon R and epsilon 0 is the product of the insulating material dielectric resistivity and the vacuum constant dielectric resistivity. From this, we can see that a dielectric material with higher value will have a larger capacitance, hence will store more energy. This is because the higher the dielectric is, the easier it can conduce electric charge. The A value represents the area of the metal plates. The higher the area of the metal plates, the more electrons the capacitor can storage, hence the higher the capacity. D represents the distance between plates. The lower it is, the higher the capacitance is. This is because the closer the plates are, the stronger the electric field will be. Another way of calculating the capacitance is by derivation from the definition of the Farad equation. We can see that the capacitance is equal to the relation between the electric charge of the capacitor and the potential difference between the plates. So, in this practical example, I have this capacitor, I will connect it to this power source. The capacitor is now charged. If I disconnect it, it will retain its charge, as can be confirmed by the multimeter. On electrolytic components, capacitance value is usually written on the side. Also, the maximum supported voltage. Connecting an electrolytic capacitor wrongly or exceeding its parameters could lead to a very exothermic reaction that could cause injury to anyone nearby. Let me show you. I will connect this component to a higher value power source than supported. Trust me, it was a loud sound. And pieces of the component could be found all around the room. Ceramic component's capacitance value is calculated from the digits on the shielding. If the capacitor only has one digit, the capacitance value is that one digit in picofarads. If it has two digits, the value are those two digits in picofarads. If it has 3 digits, the first 2 digits are values of the capacitor in picofarads and the third digit is the multiplication factor. In the specific example I have above, we can see the first digit is 2, the second 2, and the multiplication factor will be 1000. This means the capacitor has 22,000 picofarad, or also 22 nanofarad. Thanks for watching. Hope you didn't run out of capacity during the tutorial. Cheers!